I'll start sharing my screen. All right, I didn't get any questions about the probability. So I'm briefly going to go through the introduction again. Hopefully I don't get a flood of questions before the test, but yeah. All right, so insulation coordination, that's one of the main aspects of high voltage engineering, like applied high voltage engineering, where we look to protect our expensive electrical equipment to make sure it doesn't fail when there's temporary over voltages or switching over voltages or lightning over voltages. Right, and we do this by making sure that the expensive equipment has the most protection. So whether it's surge arresters, which we'll come to later, or whether there's a spark gap that flashes over before the equipment's going to break, or if the insulator 200 meters away has a lower breakdown voltage than the equipment. So it's all about coordinating such that you get the best protection for the most expensive equipment. Right, and it did go through that in the video. Right, so there's a couple of definitions. The lightning impulse withstand level, that's the new term for it. It was previously basic insulation level, BIL. That's very much an American term now. I think the lightning impulse withstand level is the IEC term. So we adopt the IEC standards in South Africa. So that is the rated withstand voltage for insulation expressed as a peak value of the standard lightning impulse under standard atmospheric conditions. There is something a little bit later, I think we look at it, called U50 or U10. U10, so 10% chance of breakdown at a voltage level is the basic insulation level. The switching impulse withstand level, that is the rated withstand voltage for insulation expressed as a peak value of the standard switching impulse under standard atmospheric conditions. All right, so both these impulse waveforms, we looked at it in high voltage 1. So the lightning impulse was 1.2 by 50 with some curves on the peak. The switching impulse was 250 by 2,500 microseconds. And that had quite a range for the tail time in particular. So the SANS or IEC does define these lightning impulse withstand voltages, the switching impulse voltages. It also defines the power frequency withstand voltage. Right, so that's in the table 1. Right, so we've got the nominal voltage, the maximum voltage, the power frequency withstand voltage, the lightning impulse withstand voltage, and the switching impulse withstand voltage. For some reason in the practical in high voltage 1, some people used the lightning impulse withstand voltage for an AC test, or a power frequency test, which means it was completely wrong. And you get ridiculous values. All right, again, I'm going to point out this nominal voltage. It's your line voltage. So to get it to phase voltage, you divide by the square root of 3. So 11 divided by the square root of 3 is 6.3 or somewhere around there. The power frequency withstand voltage is actually a phase to earth voltage. So it's the voltage that the piece of equipment can handle either phase to earth or phase to phase. but that would be phase to earth for an insulator, for example, an outdoor insulator. Similarly, the lightning impulse withstand voltage, you can only apply it to one phase at a time, and it goes to earth. That's where the flashover will occur. We'll see that just now. Right. You can see the switching impulse withstand voltage. It is not defined for the voltages below 275. That's because it's not serious. It's not going to cause a flashover. So you only look at it for transmission lines above 200 kV. The reason is that you start talking about 2 per unit at the higher voltage, and all of a sudden you're looking at very high voltages. And you're switching surges. Normally when you switch a circuit breaker, there's lots of factors involved, the capacitance of the line, if it's loaded or not, whether it's going to reflect. But you're switching at the higher voltage. It causes much worse switching surges than when compared to the lightning impulse surges. So normally we just test for that at the very high voltages. We can't do any of that in the lab at UGazadin. You need some serious equipment for that. Right, so I'm going to go through this. There are video notes for this section, including the example. But what I'm going to do is I'm just going to go through this, and then I'm going to draw out some of the equations and make some notes live. So lightning performance of transmission lines or sub-transmission lines. So the lightning may cause insulation to flash over in 2 ways. So it can strike a phase directly. That's called a shielding failure, and I'll explain that just now. But essentially, your large current from the lightning strike, it hits the line. The line is actually an impedance that causes an overvoltage, and it flashes over the insulator. And then the other one is that the lightning strikes a tower, transmission line tower, or the shield wire. That lightning, we know the tower is earthed. It travels down to earth. We also note an impedance. The voltage in that impedance can rise high enough such that it flashes over to the live line, to the phase. And that's called a back flashover, because it flashes back from the tower to the line. Okay, so equation 3, it gives the probability of a lightning stroke occurring in excess of I peak, and it's given by P equal to 1 divided by 1 plus IP divided by 31 to the power of 2.6. So that's equation 3. Okay, I hope you have these notes open, because I'm gonna start referring to the equations while I draw just now. The average number of strikes that a line may receive is given by Ericsson's equation, NS equal to NG. So that's your ground flash density into brackets 28H. That's the height of the conductor. And I'll describe that a little bit more now, plus B divided by 10. Just be aware of the units for that in the notes. The empirical equation for the attractive radius is given by RA, 0.67 HT, 0.67 I to the 0.74. So let's start looking at those 3 equations, and then I'll move backwards to that one. Right, the first one, P is equal to 1 over 1 plus P over 31. Right, so I've drawn a plot there of the probability of a lightning strike occurring over a certain amount. So it's actually a cumulative distribution. So in the hundreds range, hundreds of kiloamps, there's 100% probability that a lightning strike will occur. Sorry, it's the other way around. My bad. Right, maybe let's start with the 50%. Right, so 31 kiloamps is the median. So of all the lightning strikes, 50% of the lightning strikes are above 31 kiloamps, 50% are below. Right. I've drawn this the wrong way, sorry. Actually like that. So for 0 kiloamps, there are 100% of the strikes above 0 kiloamps will occur. So say for 5 kiloamps, only 10% of lightning strikes will occur below 5 kiloamps. 90% of strikes will occur above 5 kiloamps. If you go to the hundreds, so let's just say 100 kiloamps. Let's say it's 1%. Yeah, so only 1% of strikes will occur above 100 kiloamps. Right, so that's what that equation is saying. So if we just look at IP equal to 31, right, so 50% of strikes will occur above 31 kiloamps. Right, let's look at equation 4. Let's write down the equation first. Right, so I'm just going to draw what we've seen before. So there's phase 1, phase 2, phase 3, and we've got Earth 1 and Earth 2. We're just going to look at Earth 1 and Earth 2. H refers to the height of that conductor. B refers to the distance between the other earth wire. Right, so both those earth wires together, they collect a number of strikes. And that's equation 4. Right, let's look at equation 5. Right, so this refers to the attractive radius of any object at a certain height. What we saw when we looked at the videos of the lightning, you noticed that it always struck the tallest object. So this is the equation that kind of tells us why that happens, or how that happens. So if we've got an object, that object is height HT. Right. The attractive radius, I'm going to draw like that. All right, so all strikes that are in that vicinity of a certain current will strike the tower. So say, for example, we've got a very high lightning strike, right? It's coming down like that. If that RA will be big enough such that that lightning current will strike that tower. It won't strike the ground anywhere here. It'll strike the tower here. Now that's to do with the way that the lightning mechanism works, where the streamers start from up here. And if you've got lots of charge moving through the air for a lightning strike with high current, that electric field and that streamer is going to start at the highest point. Right. So that actually means that anything here, like this little dude, is actually protected. From a direct strike. Of 100 kiloamps. If, however, the current is very small, that attractive radius gets smaller, and he could be struck. So it could bypass that, it could strike a person or a piece of equipment or the ground near the line. So that is an empirical equation. It took years to kind of, well, a few years to come up with this. I think it was Ericsson who went to University of Natal, but I'm not sure. I'll have to find his work. Right, so I'm just going to go back 2 slides. Right, so the reason that we put the earth wires above the phase conductors is so that they can attract these lightning strikes. Okay. Right. So those two earth wires are going to capture all the high currents, the dangerous currents, but some of the smaller currents, smaller lightning currents might get past and strike the phase. Remember, this also has an attractive radius. All right, so that's quite important. That smaller lightning current, it may not cause flashover. That's the next equation that we're going to look at. So shielding failure occurs on screen sharing. All right, shielding failure occurs when lightning terminates in the phase conductor rather than the shield wire. So where it terminates on the phase conductor instead of the shield wire or the earth wire, but it also leads to flashover. Perfect shielding is given where the minimum lightning current causes flashover. And that's given by the equation. So I critical, that would be the value of lightning current that would cause flashover, is equal to 2 times U50. That's the 50% probability of breakdown for an insulator, or the flashover voltage, and Z0 is the surge impedance of the line. So we tackled surge impedance a little bit in high voltage 1, and you would have tackled it in EM theory as well. Right, the rest of the equations are just geometrical equations. So I'd go through the video note to make sure you know how to apply them. Right, so perfect shielding is where we design it such that any strike that hits the line, the phase, does not cause flashover. All right, there is an example. So in the example, there's only one shielding wire. And it looks like the phase conductor is directly below it. So when you apply equation 4, your B will be equal to 0. All right, so what I suggest for the next lecture is you go through example 1, and then you email me your queries before the next lecture, and I can answer those queries. Okay, that's it from my side. I'll see you all on Monday.